Hello and welcome back to the channel. So last time we built something really robust, a full network architecture with a certificate authority using HashiCorp Vault and free radius doing all the heavy lifting for eap-tls Wi-Fi authentication. It all worked. It worked, but it had this huge gaping flaw, the kind of thing that keeps security admins up at night. The fatal flaw of human intervention. I mean, you could issue a certificate, get a laptop on the network, no problem. But we deliberately make the certificate valid for 30 days, so every 4 weeks on every single machine, someone has to go in and manually renew it. And that's fine in a lab, but when you scale to that hundreds or, thousands of devices, the whole process just collapses. It completely falls apart. You are just setting yourself up for a constant stream of complaints. My Wi-Fi is broken, my credentials expired. It's an absolute definition of a non-scalable process. The hard part isn't making one certificate. It's managing the entire lifecycle, renewal rotation, without breaking things for the user. So today we are fixing that. We are getting rid of the manual work, the tickets, the scripts. We are going for a true set it and forget it security. And our hero today is the HashiCorp Vault agent. My name is Philip, and in today's video we are taking the next step using Vault Agent for automated certificate lifecycle management. Now, fair warning, today's episode is going to be a bit more on the advanced side, but honestly, learning proper secret management pays off everywhere. Networking, automation, DevOps, cloud, you name it. So even if some parts feel a bit heavy, stick with it. This is one of those skills that's worth having in your toolbox. So, what is the agent really? It's essentially this lightweight little demon, a client-side service that you run right on the endpoint, the laptop, the server, whatever, and its only job is to talk to the Vault. Its single purpose is to talk securely to the Vault server and then automatically fetch, manage, and most importantly, renew the secrets it needs, which for us is the client certificate and its private key. First, a quick demo of what we are trying to build. On our client device, we don't have any certificates yet. I'm starting the Vault Agent service, and voila, the client certificate and corresponding private key are there. The certificate is dedicated to our client and is valid for 30 days. We can now use that certificate to authenticate into our Wi-Fi network. Fantastic. But you may ask, what's the difference between running an agent as a service and just calling the Vault API directly? Vault Agent just sits there humming along in the background, and the goal is for the certificate and the key to just appear in the secure folder. It's not just a one-time thing, it's maintaining a rolling window of validity. It's proactively keeping the certificate fresh, not waiting for it to go stale. The certificate will be automatically renewed in several possible scenarios. Specific triggers for renewal. First, certificate is renewed when we restart the agent. It resets the clock. If we look at the certificate again, it's still valid for 30 days, but the start time has been adjusted to when the agent was restarted. Now the second trigger, the most critical one, is based on the validity threshold. The agent is constantly watching certificate it has, and when it gets close to expiring, when it hits 90% of its validity period, it automatically kicks off a renewal request to Vault. So for a 30-day certificate, that's like 3 days before it expires. And that 10% buffer is so critical. Why not 99%? Why not wait till the last minute? Because things break. Networks get flaky, servers get overloaded. When you wait till the last second and your renewal request fails, well, the certificate expires and the user is locked out. So that 3-day window gives the agent plenty of time to retry to handle any network hiccups and get that new certificate in place silently. Silently is the key word. The user never ever knows it happened. Their laptop just handled their own security maintenance while they were working. That's the dream. The last trigger is tied to its authentication token, which we are about to get into. If the token hits its absolute maximum lifetime, the agent has to completely re-authenticate. And that process also forces a certificate renewal. Before we get into more details, let's see how it's all wired. Vault agent runs as a service. Here's the service definition. You can find it in the GitHub repo. It's a very basic unit. We just start the Vault binary with the agent option and provide a configuration file. Nothing fancy here. Now let's take a look at the Vault agent configuration file. Here's the address of the Vault server. Then we have authentication. We are using AppRole. We'll talk about that in more detail shortly. What you need to know right now is that agent authenticates with the AppRole to the Vault and gets a token in return. It then stores that token in this location. It uses that token to interact with the Vault server. Lastly, Vault agent renders our certificate and a key. Here's the target location where the certificate and the key will be stored, as well as the file permissions. To render those files, Vault agent uses templates. Here's how a template looks like. You just provide the path to the secret. In our case, it's the client role used to issue the certificate, then the common name, user ID, and certificate validity. Here, we are extracting the certificate. There's a separate template for the private key. We set the same options, but extract a different field. Let's see what happens when the Vault agent starts. It authenticates with the Vault server and gets a token. It uses this token for each API call to the server. Then Vault agent renders the client certificate and key as per the template. The token it gets is short-lived. If we look it up, we'll see it's only valid for 1 minute and will expire in 43 seconds. Luckily, the agent makes sure to renew the token before it expires. If the token reaches its maximum validity, it can no longer be used and has to be regenerated. When that happens, the agent re-authenticates with the server to obtain a new token. Basically, we have two different timers to think about, the TTL and the max TTL. Think of the token like a library book. It has a short time to live, the TTL, in our example 1 minute. The agent can keep renewing that token over and over, just like renewing your library book. Keeps the session alive. But then there's the absolute maximum lifetime, the max TTL. When you hit that, the book must be returned. You cannot renew it anymore, period. So after 5 minutes, the agent easy renew option is gone. It has to go back to the front desk and check out a brand new book. It needs to fully re-authenticate. For this demo, I set the token validity to 1 minute and maximum validity to 5 minutes, but usually you would set more sane defaults like TTL to 1 hour and maximum TTL to 24 hours. Just to sum up, Vault agent turns complex secret management into a set it and forget it system. It automates authentication, token renewals and regeneration, but also certificate issuance and refreshes, all while keeping everything secure and up to date. Now that you know what to expect, let's take a step back and go through some concepts step by step. I will start with Vault client installation. I'm running Ubuntu 24.04. First, let's add the official HashiCorp repository and install the Vault binary via apt. The Vault binary is multi-purpose. Depending on the arguments we give it, Vault can act as a client, an agent, or even a server. To connect our client machine to the Vault server, we first set the server address. Now let's check the Vault server status. As we can see, the Vault server is operational and unsealed. Note that the Vault status command does not require authentication. It only needs access to the API endpoint. But to do anything meaningful, we need to authenticate. Vault supports a variety of authentication methods, including OpenID Connect, so providers like Okta, Active Directory, Google, Auth0, then Kubernetes service accounts, AWS, GitHub, and more. For now, we'll use the simplest option, the root token we received when we initialized the Vault server. Let's log in. We are in. The token is automatically saved locally, so we don't need to re-enter it for every command. If we look at the output of our login command, we'll see the token has no expiry date. It's linked to one or more policies. Policies define what a specific user or machine is allowed to do. Obviously, the root token has root policy assigned, so it has full permissions. Because we are just testing things out, we used a root token, which is like giving every single delivery driver the master key to the entire city. It never expires, it has full permissions. It's a disaster in production, a complete non-starter. You should never do that. Now that we authenticated to the vault from the client side, let's try to fetch some secrets. For that, we use the vault read command. For example, if I'd like to fetch the root CA certificate from the vault, I will just provide the read command below, followed by the path where the secret is located. There you go. Here's our CA certificate. A few things to mention. The read command is used to retrieve data from the given path in the vault. We want the result to be in the JSON format. We provide the path for the secret and use the JQ to extract only the certificate. Lastly, we save the result to a CA PEM file. Let's also extract the intermediate CA. This time I'm using a different path, PKI_int. There's where our intermediate CA is mounted. Finally, let's concatenate those certificates to get the CA chain. Blend it. Next, let's issue a new client certificate. We use the vault write command, which sends data to the vault and is used to create or update secrets. In the PKI secrets engine, certificates are issued by writing to a specific role. A role defines the rules and constraints for the certificates that can be generated, such as allowed domains, TTLs, and key usages. Let's list what role we have available in our intermediate CA. Here are two roles we created last time, one for the client and one for the Radius server. We can look at the details of a role by doing another read. This particular role allows the common name to be client Wi-Fi local and the user ID to be client. Also, the maximum validity of a certificate issued with this role is 30 days. Let's proceed to issuing a certificate. I will call the write operation. I'm pointing to an issue endpoint that dynamically generates a new certificate and key pair, and then I specify the role, common name, user ID, and the validity period for the certificate. In return, I will get a certificate and a key. I'm requesting the result to be in JSON format and store it in a file. Nice! We just got a brand new certificate and a private key. Let's extract the certificate from the JSON file and extract the key. Now, let's remove the JSON file as it's no longer needed. There you have it. We have the CA chain as well as the client certificate and a key. That's all we need to connect to the Wi-Fi network with eap-tls. The certificate is fresh and is issued for the client device. With just a few commands, we got a certificate and a key. Do you see how easy it was? That's great. However, several issues require attention. First, the token used for authentication has full permissions. We need to fix this. Token should have the least privileges possible. To do that, we'll use policies. Policies are just access control rules. They define exactly what a token can do and where it can do it. We'll set a policy with extremely narrow permissions. We'll restrict the user to be able to generate only their own certificates. We don't want client 1 to be able to generate a certificate for client 2 or client 2 to generate a certificate for the Radius server. We already have dedicated roles that limit the common name of the certificate. Now, we just need to somehow bind the user token to a specific role, so that client 1 can only call the client 1 role, client 2 can only call the client 2 role, and so on. To do that, we'll use policies. A policy defines a set of permissions, what path can be accessed, and what operations can be performed on those paths. Especially, what specific users are allowed to do. I have a policy config prepared. What do we have here? The path defines the entity we are trying to access. In this case, issuing a certificate using the client role through the intermediate CA secret engine. The capabilities define specific permissions on that path. Apart from creating a certificate, we also allow reading root and intermediate certificates. Let's create that policy. Now, check if it was created. Okay, it's there. Now let's move to the authentication tokens. I have two terminals, one with the root token and another not authenticated yet. The next step is to create a new authentication token and assign a policy to it, restricting anyone who authenticates with that token to the policy's permissions. I've set the validity of the token to be 1 hour and 24 hours for absolute maximum lifetime. After that time, renewal of that token won't be possible. Okay, so here's our token. Let's try to log in. I will copy the token, go to the other terminal, set the Vault server address and log in with it. And we are in. If we look at the token, we can see when it was issued and when it will expire. It can be used for another 57 minutes. What we can do to keep using that token is to renew it. Now the token validity resets back to 1 hour. You can renew the token multiple times until it reaches 24 hours. That's the maximum validity. After that, you need to generate a new token. Now, this token has a certain policy assigned. If we look at the policy, we see it's restricted to certain paths. For example, we can read the root CA or intermediate CA. Let's try that. I will run vault read and provide the path to the intermediate CA certificate. Works. Now, let's try to access a path that's not allowed. I will list the certificates using the root token. Works. Let's do the same with the token that's restricted by the client policy. We got a permission denied. That's because our policy does not include the PKI int certs path. However, it includes the issue client role path. That should allow us to create a certificate. Let's try that. Perfect. We got a certificate and a key in a JSON file. Let's extract the certificate and look at it. The certificate is valid for 30 days and was issued for our client. Perfect. Let's try to generate a certificate for the Radius server. For that purpose, I will use the Radius role. As expected, we got a permission denied error. Our token is restricted by client policy and it does not allow us to issue any other certificate than the one defined by the client role. How cool is that? In this chapter, we addressed a critical security issue, a token with full permissions and unlimited validity. Using the policies, shrink the blast radius if the client token ever gets compromised, as the token is not only time limited, but also has limited permissions. But how does a machine get a token? It can't just type a password. That is the exact problem that AppRole has designed to solve. Authentication without human intervention. It is the gold standard for automated machine authentication, specifically for handling the max TTL re-authentication gracefully. AppRole uses two credentials, a role ID, like a username, and secret ID, like a password. Think of it as a multi-factor authentication for machines. Let's set it up. First, let me list current authentication methods. At the moment, only token-based authentication is enabled. Let's enable authentication via AppRole. And now create an AppRole for our client device. I will name it AppRole and assign it the client policy. Now, every authentication method in Vault returns a token. AppRole is no exception. So when the application provides the role ID and secret ID to the Vault, it validates the credentials and returns a token. This token will then be used for any subsequent Vault operations. Our command specifies that the token received upon successful authentication should be valid for 1 hour. Let me quickly demo that. Here's the AppRole we just created. Each AppRole is identified by a role ID. The role ID is the stable part. You can think of it like a permanent username for the machine. There's also a secret ID. The secret ID is the dynamic part, the password that goes with it. As we have both role ID and secret ID, we should be able to authenticate. Let's copy the role ID and paste it here, and also copy the secret ID. We got back a token that now can be used to access the Vault. Let's log in using that token. I will copy it, and we are in. We can access the CA certificate, we can renew the token, we can request a new client certificate. Just to sum up, AppRole is an authentication method designed specifically for non-human automated clients. Instead of relying on long-lived hard-coded tokens, AppRole provides a more secure and flexible workflow using two credentials, a role ID and secret ID. Client presents them to the Vault, and Vault says, "Okay, you are legit. and it spits out a brand new short-lived policy restricted token. And this is really the clever bit. The role ID and secret ID pair is only used for that one moment, only once to get the token. That's the core security model here. For the next 24 hours, the client is only using that temporary token to do its work. The approved credentials are put away. They are not exposed. It massively limits the attack surface. Which brings us to the Vault agent that automates token and certificate issuance. So, once agent authenticates, it gets that precious token back. The agent stashes it in a secure location with very tight file permissions. And then it just watches it. It becomes a token watcher. It keeps an eye on that 1 hour TTL and renews it constantly long before it expires. It only goes back to using the role ID and secret ID when that 24-hour max TTL finally hits. It's just relentless token management. Let's first create a folder where the agent will store the token. Let's change the permission and owner of that folder. We need 4 more files. A file containing the role ID for our AppRole. You can get it by reading the role ID from our AppRole. Then a file containing the secret ID for our AppRole. You can get it by calling write on the secret ID path. Now, the main configuration file, the Vault agent HCL, that can be obtained from the GitHub repo. It's the blueprint for everything. It tells the agent the Vault server address, and critically it specifies the AppRole authentication method. It also points to the files on disk where the agent can find that initial role ID and secret ID. We also need to create folders where credentials will be rendered. Now the templates. The agent gets a big blob of data from the Vault, but we need a clean, readable file, a PEM file and a key file. This is where the agent gets really powerful. When Vault issues a certificate, the API response is this big JSON object. It has the certificate, the private key, the CA chain, everything. And the templates are like instructions of parsing that JSON. And inside that template, you tell agent which Vault path to call. And you define what you want, like common name for the cert. And then you tell it which field to pull out. You use a little bit of Go template syntax, something like data.certificate, and that tells the agent, find the certificate field in the JSON response and render only its value onto the output file. So it's not just dumping the whole JSON file, it's surgically extracting the exact piece of data you need and putting it into a clean file that, say, your Wi-Fi client can actually understand. And the key template does the exact same thing. It pulls out the data for the private key field. The agent writes both files, sets the right permissions, so the private key is locked down, and you are done. Let's also get the systemd service definition, as well as an environment configuration file for the service. Here's how the configuration file looks like. Templates, credentials, agent configuration. Then let's ask systemd to rescan all unit files. We can now enable the service and start it. Our Vault agent is ready. We secure the credentials with AppRole, but there's one final, really fundamental piece missing. We've been doing all this over plain HTTP. We have been up to this point. Sending secrets over an unencrypted channel is, well, it's a complete non-starter. We have to enable HTTPS. Okay, so we need to secure the Vault server itself with TLS. That means issuing a server certificate for it. We can use our own CA that we already built, but first we need to create a new dedicated server role in the PKI engine. This will allow us to issue certificates specifically for our Vault server. Now let me issue a certificate for our Vault server. I will include both the common name and the IP address as sans. Perfect. Let's extract the certificate and private key from the JSON response. Now we need to copy these files to our Vault server's TLS directory. In our Docker setup, this would be the vault/TLS directory. Next, I need to update the Vault server configuration to enable TLS. I will add these lines to enable that. Now, let's restart the Vault server to apply the new TLS configuration. If we look at the logs, we see TLS enabled. Now let's test our TLS setup. First, let's try connecting using HTTP, as we did before. That failed because we disabled HTTP access. Now, let's try with HTTPS. We got a certificate validation error because our client doesn't trust the CA that signed our server certificate. Let me provide the CA chain to our client. Excellent. Now we have a secure TLS connection between our client and the Vault server. The connection is encrypted and both client and server can verify each other's identity using certificates. All HTTP requests are rejected. Let me also update our Vault agent configuration to use HTTPS. I will change the address line to use HTTPS and specify the CA chain file so we can validate server certificate. Let's also update the environment variable file for Vault agent service, changing the address to use HTTPS and specifying the CA chain file. Now, let's restart the Vault agent to pick up the new configuration. All looks good. We can see the agent can still fetch certificates. Excellent. Our automated certificate lifecycle management is now working over a secure TLS connection. This completes our security setup. We now have Mutual TLS authentication between client devices and the radio server, secure HTTPS communication between Vault clients and the Vault server, and automated certificate lifecycle management using Vault agent and proper access control through policies and AppRole authentication. So let's just recap. We have an agent using an AppRole to get a short-lived token. It's using that token to automatically renew client certificates based on least privilege policy. And all of that communication is happening over a verified end-to-end encrypted HTTPS channel. The entire system is now set it and forget it. The risk of an expired certificate taking down your network is just gone. We moved away from a brutal manual process to a truly resilient production-ready system. You know, this whole time we've been focused on one use case, getting certificates onto laptops for Wi-Fi. It's all about endpoint identity. But this model, this pattern of an agent plus AppRole, it's not just for certificates. It's a generic pattern for automated secret delivery. And that raises a really important question. What if you applied this exact same architecture to something else entirely? Say, rotating the database credentials for a critical application server, or rotating API keys for a microservice. So how would your templates have to change to handle that? And what about your policies? What if you need those database credentials to rotate every 15 minutes instead of every 30 days? How does the constant high-frequency rotation affect your application stability? That's the next level of this automation journey. Thanks for watching, stay safe, keep learning, and I'll see you next time.